In this tutorial, we will explore the concepts of resistance and resistivity in the context of electric circuits. These two properties are essential for understanding how electric current flows through materials. Let's break down these concepts step by step. Understanding current. Current, denoted as I, is the flow of electric charge through a conductor, such as a wire. It is measured in amperes, abbreviated as A. Imagine water flowing through a pipe. Electric current is similar, but instead of water, electric charges move through the conductor. Ohm's law. Ohm's law is a fundamental principle in electrical engineering. It states that the current I flowing through a conductor between 2 points is directly proportional to the voltage V across those 2 points and inversely proportional to the resistance R of the conductor. The formula is I equals V divided by R. This means if you increase the voltage, the current increases. If you increase the resistance, the current decreases. Power. Power, denoted as P, is the rate at which electrical energy is transferred by an electric circuit. It is given by the product of voltage V and current I. The formula is P equals V times I. Power is measured in watts. This tells us how much energy is being used or produced by an electrical device. Resistance. Resistance, denoted as R, is a measure of how much a material opposes the flow of electric current. The unit of resistance is the ohm, symbolized as omega. Think of resistance as friction for electric current. It slows down the flow. The resistance of a conductor depends on several factors. 1. Length, L. The longer the conductor, the higher the resistance. Resistance is proportional to L. This means resistance is directly proportional to length. 2. Cross-sectional area, A. The larger the cross-sectional area, the lower the resistance. Resistance is proportional to 1 over A. This means resistance is inversely proportional to the area. 3. Material. Different materials have different resistivities, affecting the resistance of the conductor made from that material. Formula for resistance. The resistance of a conductor is calculated using the formula R equals ρ times L divided by A. Where R is the resistance, ρ is the resistivity of the material, L is the length of the conductor, A is the cross-sectional area of the conductor. Resistivity. Resistivity, denoted as ρ, is a material-specific property that quantifies how strongly a given material opposes the flow of electric current. It is measured in ohm meters, symbolized as omega m. Different materials have different resistivities. For example, metals typically have low resistivity, which means they conduct electricity well, while insulators have high resistivity. Factors affecting resistance. 1. Length, L. If you increase the length of the conductor, the resistance increases. Think of a longer hosepipe that makes it harder for water to pass through. 2. Cross-sectional area, A. If you increase the cross-sectional area, the resistance decreases. This is like a wider hosepipe allowing more water to flow through easily. 3. Material. The type of material affects resistance. Copper, for example, has low resistivity and is commonly used in electrical wiring, whereas rubber has high resistivity and is used as an insulator. Visual representation. Imagine a cylindrical conductor with length L and cross-sectional area A. Current I flows through the conductor. The resistance R is influenced by the length and area of the conductor as well as the material's resistivity ρ. Summary. Resistance, R, depends on the material, resistivity, the length, L, and the cross-sectional area, A. Resistivity, ρ, is an intrinsic property of the material and affects how much resistance the material provides to the flow of current. Understanding these principles helps in designing and analyzing electrical circuits effectively. Whether you're working with electronics or large electrical systems, knowing how resistance and resistivity work will help you predict how current will behave in your circuits.